All right, now that we have defined all of the angular descriptions for motion in terms of angular position, angular displacement, angular velocity, and angular acceleration, we'd like to look at this special case where the angular acceleration is constant. So basically, the case where this angular acceleration value is a constant value, and that means that the object is rotating, and as it rotates, it's speeding up or slowing down at a constant rate. And so if you recall, when we had linear motion, we had the kinematic equations for linear motion, and that was when we had constant acceleration. And under those conditions, we had a set of 4 equations that we could use to make predictions about the motion. So it turns out that we have those same representations for rotational motion, and if we think about how these are connected with each other, in linear motion we had displacement or position, and so in rotational motion we have angular position. For linear motion we had velocity, and now we have angular velocity, and for linear motion we had acceleration, and now we have angular acceleration. So if we went back and we wrote down the kinematic equations, the first kinematic equation for linear motion was the final velocity is equal to the initial velocity plus the acceleration times the time. So in terms of the rotational variables, if I replace final velocity with final angular velocity, initial velocity with initial angular velocity, and acceleration with angular acceleration, I get the first kinematic equation for rotational kinematics. So we could do the same thing with all of the other equations of motion for the kinematic equations and just make those substitutions, and we have this relationship between all of the variables of motion under constant angular acceleration that we can use to solve problems. And basically this works out because of all the connections between these variables, right? So linear velocity is the rate of change of the position, and angular velocity is the rate of change of the angular position with respect to time. Acceleration is the rate of change of the velocity with respect to time. Angular acceleration is the rate of change of the angular velocity with respect to time. So here is actually a picture from a textbook that shows these connections. It's basically similar to what I had on the previous slide, and it just shows how those equations are basically the same, where we have this connection between the variables. So let's look at an example and see if we can solve for some unknowns in our expressions. We need to read it carefully, we need to identify what's given, and then see what we can how we can go from there. So we have a bicycle wheel that's rotating at an angular speed of 30 radians per second, and it comes to rest in a time of 6 seconds. What is the angular acceleration of the wheel, and what angle does the wheel rotate through as it comes to rest? Assume the wheel slows down at a constant rate. So that's important because this implies that the acceleration, angular acceleration, is a constant. So these pictures are a little bit harder to draw because it is an object that's rotating about an axis, but I could imagine that I have a bicycle wheel and it's rotating around, and at first it's rotating at 30 radians per second, and it has some axis of rotation through the center. So the initial angular velocity is 30 radians per second. It says that it comes to rest, so the final angular velocity is 0. The time it takes to come to rest is 6 seconds. And we're interested in determining what is the angular acceleration, and also what angle does it travel through. So if we assume that it starts off at an angle of 0, which we can make that assumption if they don't tell us, we're also interested in determining the final angle. So if I go to the kinematic equations for rotational motion, I see that the final angular velocity is equal to the initial angular velocity plus the angular acceleration times the time. It comes to rest. The initial angular velocity is 30. I'm interested in knowing the angular acceleration when it takes 6 seconds to stop. So if I move the 30 to the other side, and now I can divide both sides by 6, I get that the angular acceleration is minus 5 radians per second squared. So I've made an assumption here that this object is actually rotating in a counterclockwise direction to start with. I've made these both positive, or well, it's 0, but it's still positive direction, and that's fine. I determined that the angular acceleration here is negative, so it has the opposite sign as the angular speed, and therefore this represents slowing down. So it has the opposite sign, just like if you had linear motion and the acceleration had the opposite sign for one-dimensional motion, it would be slowing down. For part B, we want to determine what angle does it travel through. So I now know the angular acceleration. So I can use any of the kinematic equations for rotational motion that involve the final angular position. And so without using the angular acceleration, I could use the fact that the final angular position is the initial angular position plus 1/2, the initial angular velocity plus the final angular velocity times the time. The initial angular position is 0. The initial angular velocity is 30. The final is 0, and the time is 6 seconds. So the final angular position is 90 radians. So it travels through a distance of 90 radians, and of course we could convert that into revolutions if we wanted to, or degrees. All right, let's consider another example. This one, it says that the drive propeller of a ship starts from rest and accelerates at 0.035 radians per second squared, and it accelerates for a time of 18 seconds. It then continues to rotate at a constant angular speed for 900 seconds before it begins to slow down at a rate of 0.02 radians per second squared. We want to find the total angular displacement of the propeller when it finally comes to rest. So first, we have the object, the propeller is accelerating. Then it's moving at a constant speed. And then it slows down. So each one of these can be represented by a constant acceleration motion, but we have to look at each one of them separately. So I would break this up into 3 different motions. So I have motion 1, motion 2, and motion 3. And so what I can say about motion 1 is that it starts from rest. So the propeller has an initial velocity of 0, and I'm going to use radians per second because that's what's being used. It accelerates at a rate of 0.0350 radians per second squared, and it does that for a time of 1,800 seconds. That's the first part of the motion. It then continues to rotate at a constant angular speed for 900 seconds. So this part of the motion has 0 angular acceleration, and I know that whatever the initial speed is in terms of its angular speed, it's also the same as its final. I don't know what that is, but I do know the time interval here is 900 seconds. And this is the time interval for 1. And then finally, for the last part of the motion, it says that it slows down at a constant rate. So it has angular acceleration, but it's slowing down, so it's got to be a negative angular acceleration. and then eventually it's going to come to rest. So the final angular velocity is going to be 0. And what I want to know is what is the total angle that it goes through during this entire motion. So I'd like to say what is the final angular position after motion 1. So I'm going to say that it starts off at 0, and I'd like to know what that final angular position is. So I can use one of the kinematic equations and I can solve for that. So for motion 1, I can say that the final angular position is just equal to the initial angular position plus 1/2 the angular velocity initial plus the angular velocity final times the time. So now I have a problem, right? Because I wasn't thinking ahead, and I don't know what the final angular velocity is. So I actually need to go with a different expression. So I can use the fact that the final angular position is the initial plus the initial angular velocity times the time plus 1/2 the angular acceleration times the time squared. The initial position is 0, the initial velocity is 0, and so the initial position is just 1/2, or the final position, excuse me, is 0.0350 radians per second squared times the time of 1800 seconds squared. So the final angular position ends up being 56,700 radians. So, you know, it's a propeller and it's on for quite a while, so I'm not surprised that it's a pretty large number. So we now know that this is 56,700 radians. So now perhaps we can move on to the second part of the motion where it moves at a constant speed. And so I do know the angular acceleration, I know the time, and I also now know what the initial position is. The initial position is going to be 56,700 radians. And I'd like to know what is that final angular position. The problem is I don't know anything about what the initial and the final velocities are. But I do know that this is a continuous motion. So if I could solve for what the final velocity was for motion 1, then that value would be the initial and the final velocity for motion 2 because it takes over and it starts spinning at a constant speed. So I do need to find that value. So I'm actually going to erase down here, and let's see if we can determine what that final angular velocity is. So the final angular velocity is going to be the initial angular velocity plus the acceleration times the time. It starts from rest. The angular acceleration is 0.035, and the time is 1800 seconds. So this ends up being 63 radians per second. So we now know that this is 63 radians per second. And if that's the final velocity for the first motion, it becomes the initial velocity for the second motion, and because it's traveling at a constant speed, it's going to also be the final. So now that I have that information, I can figure out what the final position is for motion 2. So I know the time, I know the velocity, so I could use the fact that the final angular position is equal to the initial angular position plus the initial angular velocity times the time plus 1/2 the angular acceleration times the time squared. There is no angular acceleration, so that is 0. And so the final angular position is just the initial angular position plus the angular velocity times the time. And so I end up getting 113,400 radians. So I now know that after the second part of the motion, the total distance traveled angularly is 113,400 radians. So now I can move on to the third part of the motion. In the third part of the motion, I know that the initial angular position is going to be 113,400 radians. And I also actually know what the initial angular velocity is. Because this is a continuous motion, whatever the final angular velocity was for motion 2, that becomes the initial for motion 3. So I have enough information now that I can solve for the final angular position after all 3 of the motions. So I can use one of the rotational kinematic equations for that last part of the motion. And if I do that, I could use the fact that the final angular velocity squared is equal to the initial angular velocity squared plus 2 times the angular acceleration times the final position minus the initial angular position. So it comes to rest. The initial angular speed is 63. The angular acceleration is a negative 0.02. And this is just equal to the change in the angle. I'm running out of space, so I'm going to write it that way. So if I move the 63 to the other side and I square it, I get negative 3969 radians squared over second squared equals minus 0.04 radians per second. And then this is the final minus the initial angular position. Divide both sides by negative 0.04 and I get 99225 radians. And that has to equal the final angular displacement or position minus the initial. And the initial was what we left off with in motion 2, which is 113,400 radians. So if I add that to both sides, I get that the final angular position is 212,625 radians. So this is similar to looking at the motion of an object that is like a car that's accelerating, moving at a constant speed, and then slowing down. It's just that it's rotational motion instead of linear motion.